So hey everybody, I am Shivani with GoEngineer. Thank you for logging into our webinar, Rotating Components in our Computational Fluid Dynamics program called Flow Simulation. Today we'll set up 3 separate analyses on a rotating fan. First, we'll drive RPM and determine flow speed. Second, we'll drive flow speed and determine RPM. And then third, we'll figure out how to do a transient sliding mesh technique for unsymmetrical domains. These are both examples of rotating parts we can analyze in flow simulation. But what about them makes them feasible to analyze? On the left, we have an impeller. The blades are rotating at RPM, driving the fluid to rotate and exit out of this outlet. And on the right here, we have a turbofan. So same thing, it's spinning at RPM, the other direction, and driving fluid, causing it to rotate, same thing. So what makes them similar is that they both rotate about a center line and drive fluid flow. This is the primary use case of rotating regions in flow simulation. But what makes them different from each other, from other examples? Take a look at the distance between the blades and the outer casing here in the impeller. It varies during the full 360 degrees of rotation. This requires us to use a very special kind of rotating region called a sliding mesh. This takes all the mesh elements touching those blades and forcibly causes them to rotate. We are at that point emulating the blades actually moving and forcing the fluid to flow. We'll get into that in a little bit more detail later, but that is one type of rotating region that we have. In the turbofan, we don't see that variable spacing, so we don't need to use a sliding mesh technique, which saves us calculation time. Instead, what we use is the averaging technique. This is the blades themselves are not moving. We are saying that the fluid around the blades has reached a steady state. So any fluid that is in the area that the blades could affect is forcibly rotated at RPM. So again, this one on the right is for symmetrical casings around the blades and meant for more of a steady state type analysis. Again, we'll see both in a little bit more detail, and we're going to start with the one on the right, more of a turbofan type setup. Now, again, thinking a little bit further on what makes these examples different, the turbofan is also attached to a plane, which is flying at velocity in a direction. Now, in flow simulation, we don't simulate the parts actually translating or moving like a kinematic way. Like a plane flying forward or a piston moving up and down. Instead, for examples like this turbofan or a car driving on a road, we tell the fluid to flow in toward the object at the same speed the object is actually driving forward. So in the turbofan, we have fluid speed flowing towards it. So that's just 2 examples there. We're going to move on to the example we'll be using in this webinar, which is a fan, and it's an EBM Pabst fan, and I downloaded this from GrabCAD. Now, there are 2 ways that this fan can be analyzed. First, we are either driving the RPM and producing a flow rate, or we are blowing air across the fan, and by the shape of the blades, we're producing RPM. We call this second case fluid structure interaction, or FSI. FSI is not technically possible in SOLIDWORKS Flow Simulation, but by taking advantage of optimization techniques, which I will show you in the webinar, we can still get answers like this. So starting with our first setup. For problem 1, we will introduce the overall flow simulation setup and kind of guidelines, while saying, I know what the motor torque is. I know the motor torque I'm applying onto the fan. what RPM would that produce due to reaction forces like torque on the fan itself? What overall airspeed is produced by the fan rotating? So let's go ahead and take a look at that. I'm going to switch over to SOLIDWORKS and first introduce to you the assembly that this is in. First of all, I have this tube. This is acting as my wind tunnel around my fan. And within it, I do have the fan itself. It has been fairly simplified. That hub and the rest of the motor is mostly gone. And I do that for calculation time. The simpler I make the model, the faster I can get to an answer. Now to start with my very first project on this fan, I would go to my wizard and go through my steps. Now the first thing here in the unit system, many people are going to put in RPM or want RPM in the units of RPM. That's not the defaults. So I recommend you go to Loads in Motion and find Angular Velocity. From there, you can always override that unit system to RPM. Okay? And the next, this is really the big thing here. First of all, I am only concerned about the airflow around the fan inside the wind tunnel, not what's going on in the rest of my SOLIDWORKS domain. So I'm going to consider this internal. Other than that, I'm just considering the fan rotating. So we'll take a look at rotation. And there's that averaging method that I discussed for the turbofan, which is the one we use when we want symmetrical results and we can deal with a more steady state solution. That is so far what I can do for this fan, so I'm going to start by using this local regions averaging. I hit next. I pick my fluid. I'm going to select air. You can of course select any fluid, even custom fluids. I'll stick with the defaults here. I am saying that I'm not having heat transfer outside of the wind tunnel. And I'll say the walls are relatively smooth. And overall, I'm having the system start at steady state in temperature, 1 atmosphere, about 20 degrees Celsius. Perfect. So I hit finish, now create that project. Now, of course, I already have one created. So let's go ahead and take a look at what else gets set up. Because after you create that wizard, you get this tree on the left-hand side. I have a couple categories here where I filled things in. If you are new to the system and are wondering why you don't have the same things in your tree that I have, right-click on your project name and go to Customize Tree. You can turn on more options. Okay, now having set up the wizard, the next thing I'm doing is setting up the rotating region. So I'm just going to select this. I can see that there is a cylinder surrounding my fan. This is a physical part file or body that I modeled into the assembly and just hid from view. When you guys are making these, this is the region that you expect to be affected by the fan blades. You don't want this to accidentally cross over other components. So you'll see that it is smaller than the wind tunnel. And again, this is the area that the fluid will be forced to rotate at RPM. Okay? Now, that's just the volume itself. When you want to select it in the rotating region, I recommend you go to your flyout tree and select the solid bodies or part files from your folders. Second, if I take a look at these green-blue arrows in the center of my rotational region, it is telling me which direction the fluid is going to rotate. So in this case right now it's rotating like this. And of course the way that I drive that is with positive and negative symbols in the angular velocity. So for example, if I switch that to negative, you can see that arrow, that rotation arrow, change direction. Now, why didn't this arrow in the middle change direction? What does that mean? So this is just the direction considered for positive torque, okay? It's not the direction the fluid is actually going to flow. the direction the fluid is actually going to flow depends on the shape of the fan blades, right? So that was just positive direction of torque, what that was telling us. Right-hand rule. Okay, so that's my rotational region setup. We're pretty much all the way done at that point. The last main step is just setting up an inlet and outlet condition on the wind tunnel. I have done 14.7 psi on the inlet and outlet. So all the fluid speed, all the pressure drop will be created because of that fan speed. Now, as part of that problem 1 setup, I had asked, I know what the motor torque is. I want to determine RPM. I want to determine flow speed. So, using goals inside of flow simulation, I can measure not the motor torque, but the torque on the fan itself because of the fluid. So when I have the torque of the fluid matching the torque produced by the motor, then I know this is likely what the RPM of the fan is going to be. Okay? Now, if you want to set up these torque goals yourself, you can see that I set up 2 of them. One of them is a global goal. So that's the torque from every single face in the entire assembly, including the wind tunnel. And then for my surface goal, where I went and found torque, I selected the faces that carried the majority of the torque, which was majority of the faces that are on the fan blades themselves. I have pulled up both of them so that you can compare results as we look later on in the result files. Okay, we go ahead and we give that a run and I get my results. Let's go ahead and look at this couple. All right, so at a glance, it does look as we would expect. The flow is moving this way. It's starting to swirl as it hits that rotational region and building up some stagnation regions there in the back, as I'd expect. Maybe you want to look at something besides velocity, perhaps pressure. Certainly I can get an idea of the pressure drop across the fan blade. Looks to be about 0.2, 0.1 psi. Now that's nice, but what is my airspeed? What is my RPM? Well, I defined the RPM as 1500 RPM. Does that match the motor torque that I expected? How do I figure that out? Well, I've got some numerical results down here. My goal plots will very quickly tell me that the amount of torque due to airflow on the fan blades is about 95 inch-pounds. Okay, well, my motor wasn't 95 inch-pounds, acting at 40 inch-pounds, so I guess I have to start guessing on RPM until this number matches. Now, when I say guessing at RPM, you don't have to do that manually. That's where we get into this idea of optimization studies. Now, for the very first time I do this, I'm going to set it up from scratch. The other times, I'm just going to jump right into it. Now, to set up an optimization study, you go to Tools, Flow Simulation, Solve, and then New Parametric Study. All right, you have a few different options here on the left. Because I know what I'm aiming for, which is a certain motor torque or torque on the fan, I'm going to choose Goal Optimization. Then I choose what is allowed to vary. In this case, that is the angular velocity of the fan blades, what RPM is that spinning at. I can have it go from 100 to 100. Criteria, this is the torque I'm aiming at, so I go pick my goal, I pick a particular one, and say I'm aiming for, let's say, negative 40 inch-pounds. And again, negative is just the direction. And then plus or minus some variable. We go to my third tab, Output. I pick what I want to track, just for my own personal knowledge. And then I go to Scenario, and I say the maximum amount of time it's allowed to run, and I hit Run. SOLIDWORKS iterates as many times as it needs until it finds me an answer. Like so. I'm going to scroll over here to the right. We will see we hit that negative 40 inch-pounds at about 900 RPM. So one of these goal optimizations could get me an answer there in about 16, 17 iterations, where I could just leave this over lunch and come back and have an answer, compared to having to do this manually in Excel. Good stuff. Now that's kind of the first setup. We'll take a look at this again for our second problem. This is kind of the inverse, right? Where we are approximating fluid structure interaction, or approximating FSI. Here, we are going to define a flow rate across the fan blades. And in reality, the fluid pressure, or torque on the blades, causes the fan to begin spinning. But in flow simulation, I can't have that fluid structure interaction, so instead, I'm going to measure the torque on the blades, adjust the RPM, until the torque is approximately 0. Very similar setup, just different kinds of optimization that we're doing. So, same setup. I come over here to my next project. Nothing has changed in the fan and in the wind tunnel. Nothing has changed in my initial wizard. I'm still using a local region averaging. But I've chosen some random RPM now. Now I'm using 20 RPM. And my boundary conditions have changed to just have a default 14.7 environmental pressure on the outlet. And the inlet now is forcing a flow rate of 100 inches per second into that wind tunnel. So again, the fluid is going to be driving the fan. That's the only change to my setup. I go through and I get various results again. Now, when I go and look at my torque values, let's look at that over here. I can see that my overall final result ends up at about 2.8 inch-pounds. So the fan, 20 RPM is incorrect. The fan would still be forced to either slow down or speed up. I don't know what is true yet. So that's where optimization comes back into play again. So this time, in my optimization study, I vary my RPM, just like before. Tracking my torque goal, but this time, look at that target value. I'm aiming at a torque of 0. A little bit of plus and minus. Tracking my parameters, I give it a run. This study only needed 3 iterations to pretty much get to an answer. It ran my max RPM, my min RPM, and guessed at 180. And at 180 RPM, there was about 0.06 torque on those blades. Not too bad at all. So very quickly, I'm able to get an estimate on how fast that fan is likely rotating. What I would do from this point is double check this, run finer meshes, maybe more detailed studies with the rest of the fan. To do that, I can actually right-click on Design Point 3 and create a new project based off of it. So I don't have to set anything up from scratch in order to test that number. Now for our last problem, we're going to get a little fancier. So far I've been running a very simple assembly where the fan was held in a featureless tube. In this case, I have modeled in some ribs, which has made the region around the fan blades unsymmetrical, right? You see that here, just like the impeller. It is highly recommended when I have an unsymmetrical region like this that I use the sliding mesh technique, where the mesh rotates at RPM instead. This way we are truly simulating the fan blades actually moving, essentially. And so we can capture the effect that they'd have as they move past the ribs. This is a much more accurate way to simulate the fan blades, but it does take a longer time to solve. So I'm going to teach you guys some speed techniques as you do this for your early design iterations. So just to repeat, we are going to define an RPM that fan blades are spinning at and determine things like flow rate, pressure drop, etc. So again, this one's not looking very different. Go ahead and load this. Because the real changes are in the wind tunnel. But as I'm setting up the wizard, hitting next and going through my units, I get to this section and I say, okay, I need to do that sliding mesh option. So I'm not using that averaging method. In the drop down, I'm going to sliding. And I immediately get this pop-up. Because I'm no longer making the assumption that the fan and the fluid around the fan has had a long enough time to reach steady state and all be rotating at the same speed, I can no longer make that assumption. I have to have the fan blades forcibly pushing on the air. So it has to start from a velocity of 0. So time is now a factor in the calculation. So it's asking me to turn on time-dependent analysis. Okay. So I went ahead and turned that on. Right away, it's asking me for the overall time for the study. This is the first big question on how long this is going to take us to solve, whether this is going to be an overnight solve or something I can do in 20 minutes. When you're doing your initial design iterations, I recommend you run this no more than 2 full rotations of the fan. Okay? Initial design iterations, 2 rotations of the fan. That's enough to get a very good idea of what the overall flow is doing. As you get to your final design iterations, where you need to be more detailed, please run it for more than 2 to make sure you're getting steady state results. So 5 rotations, 10 rotations, something like that. So do some hand counts, figure out how many seconds per rotation based on the RPM you're applying. I'm going to do 1500 RPM, which is about 0.04 seconds per rotation. So by my recommendations, that means I should put in 0.08 seconds for a total time. Okay? Now, personally, I leave output time step at 0, and I'll explain that in further detail in just a moment. But the rest of the wizard is all defaults, and I would close this and be done. Okay? And then that gets me here to my tree. My RPM is, as I said, 1500 RPM. I still use the region, that model that I had done before. It's very important that this region only encloses the areas you expect to spin. Okay? I know some people have rotors and they have stators around the fan itself. Anything inside that rotational domain is going to be forced to rotate at RPM. So please make sure this region only encapsulates your rotor. To go into further detail on that, mine is a simple cylinder. The only requirement Flow asks of you for this rotational region is that it's axisymmetrical so that it can rotate. Okay? So even if it's a funky shape like that, that's okay as long as it's axisymmetrical. Really great drawing skills. Awesome. Other than that, we've got the 14.7 psi on my inlet and outlet. Same torque goals as before. Now, time savings. I said this was important, especially for iterations and especially with this time-based transient sliding mesh technique. I recommend you right-click on your input data folder and go to Calculation Control Options. Right away, you can see my physical time, 0.08 seconds. That's the 2 rotations of the fan blade. Go to your Solving tab and go to the Manual Time Step option. By default, this is going to be on automatic, which is good for accuracy and bad for solve time. So as you're doing iterations, switch this over to Manual. My time step is based on having a total output of 100 steps. That seems to be enough of a refinement to capture the flow correctly. Be aware I'm adding in error because now I am forcing it to make time steps potentially larger than actual perturbations in the flow. So I'm losing access to some perturbations that are happening. I'm losing accuracy. So everything with a grain of salt, all right? We're doing this for early design iterations to quickly get to answers so we can get an idea of our results. Final answers, please go back to auto and let that be accurate. Fourth tab. The saving tab is less important for your calculation time, but more important for your hard drive space. By default, this periodic will be checked, and it will be saving a full set of flow simulation results. It's all pressures, velocities, etc. for every single one of those time steps. So in my case, that would be 100 sets of results. These results can easily get to multiple gigabytes in size, and I don't want to waste my hard drive space on something like that. So a personal preference is actually to leave this off. What will happen by default is I'll get a full set of results for the very last time step, 0.08 seconds. And then I additionally turn on this transient explorer. Okay? This gets me what I desire, what I choose to track visually over all 100 time steps. So in this case, I've chose to only track pressure. This helps me get nice animations and gives me sanity checks on what the overall fan is doing and system is doing. Other than this, for visual results, my numerical results that I have in my goals, those are the only other thing getting tracked for all 100 time steps. Everything else I'll only get for the last time step. Excellent. I can go into that in more detail as we get into Q&A if you have any questions. But other than that, I would give it a run. This setup took me about 20-30 minutes to solve this, which wasn't too bad. I very often see these kinds of calculations with good mesh go to about 2 hours, sometimes overnight. And yeah, let's go ahead and take a look at some of the results just for the fun of it. So there's my pressure at that 0.08 seconds. I cannot load any previous seconds because I didn't save any. But if I go to Transient Explorer, since I did turn that on, I get access to animations, which I can then play. We see that spinning about 2 times. What's up with this secondary fan blade? What the heck is that? That's the original model, okay? Flow simulation isn't going to show the model moving, it's showing the results moving. Like so. So with SOLIDWORKS Flow Simulation, we calculated fluid and pressure effects by the fan, and reaction forces and torques back onto the motor. And then by taking advantage of mesh techniques, optimization studies, and transient analysis, we can obtain very accurate results, and if we're careful, we can get them very efficiently as well. First of all, I recommend you do 2 local meshes, okay? The first is applied to your fan blades themselves in some form or fashion. I selected all the faces of the fan blades. Now, in this partial area here, this partial setup, this is cells that are touching fluid and solid. Now a cell is more like a square kind of thing. So by forcing these to get smaller, I'm going to better capture the strange geometry of these fan blades, okay? You'll see I didn't click all the back faces as well. I don't think that's necessary. By forcing the mesh to get smaller around this face, naturally it's going to be smaller around the back face as well. So I've made that mesh 4 times smaller. Now, a second recommendation I say you should do, create a second local mesh and select the rotating region around your blades, and make sure to refine the fluid cells a couple times. Now I'm saying refinement. I wish I'd had my PowerPoint slide on this, but essentially this is a mesh cell. It's a cube. When I tick this 1 level over, I cut this cube into 8ths. And then I go that 1 more time, and then I cut up into whatever that number is. Over and over. So the mesh blows up very quickly. You don't have to take it all the way to 9 to get a good result. As I'm testing things out, I'm normally starting at 3 or 4 and seeing if that's small enough and then going further if I need to. Now I have picked 3 here. My idea is that for my initial iterations, I have at least 4 to 5 mesh cells across the beginning to end of that rotating region. 4 to 5 at least. Now, as I want to get more accurate results, please bump that up. The smaller you make your mesh, the more likely you are to capture perturbations and stagnation regions and correct pressure drops, etc. Now, I just discussed the local mesh. The way that I like to look at the mesh in order to test it for being small enough, I take advantage of surface plots and cut plots. So I'm going to start with a cut plot on the right plane. Yeah, we'll go with that. I don't show pressure or anything like that. I just look at this filter for mesh. I go to options and I uncheck use CAD geometry. Okay. CAD geometry will perfectly trace the fan blades, perfectly trace my geometry the way it looks exactly right now. By unchecking use CAD geometry, I see what the solver actually sees. So it's imperative that I uncheck this and make sure my fan blades got captured appropriately. So hit OK. I'm going to go ahead and hide this fan again so we can get a closer look. And as I zoom in, I can see that that shape is very smooth along that fan blade. I did capture that region well enough. Where there tend to be problems in general, fillets, round faces, especially swoopy faces like that, so I'm glad we did that mesh refinement. Does this match the 3 to 4, what did I say, 4 to 5 cells across the thickness that I asked? Yes, it does. I have over 5 for sure, so I've met my minimum. My crash course in the meshing. There's a lot with meshing, of course. You saw so many slider bar options there in my setup. Know that we're here to help you. If you're brand new to Flow and you just need someone to talk you through meshing options, go to GoEngineer's website and look up application mentoring sessions. We can screen share with you, we can talk it through. Technically, you can get away with it crossing the boundary. There are some tricks, okay? So let's say across the stator, I can apply a boundary condition, wall boundary condition, my face, and say it's a stator. So the fluid flow touching that face should still be 0, or velocity of the face should still be 0, and then have a boundary layer, etc. Where it breaks down is when you're using the sliding mesh technique, where it's forcing the part to rotate. If I had accidentally made that rotation region big enough to include the ribs would have rotated also, okay, even if I applied a stator condition on them. So, to kind of summarize that answer, I highly recommend your rotation region only enclose the rotor just for human error, okay? Just to prevent any errors. So the most sensitive thing absolutely is mesh. You could do a terrible mesh and a 100-second solve time and still solve reasonably quickly. So mesh, absolutely the critical thing that increases solve time. Now, because of fan blades generally being thin, and then combining that with the time-based analysis, that's where solve times tend to blow up. So that's why we keep times, like amount of rotations, lower, because we're required to have that mesh higher. So I'll say that again, mesh is the really critical thing. Thank you guys so much for coming. See you guys next time.